So this is very exciting. So this is a very exciting day for me because today we're going to start quantum mechanics. So this is a very exciting day for me because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I've got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
हां लागला काही फरक पडलाय हां So what is the mass? What kind of masses are we talking about? So that's typically a mass of electron. Find out how small it is. Then we talk about Planck's constant, which is a constant which relates energy, quantum of energy with h omega. So what is h? Two questions. What is the value h or h cross, which is divided by 2 pi, the constant is absorbed h cross omega, and what is the dimension of that. Somewhere this question of dimension will come, and it could be very confusing because most of us use e to the power of interchangeably because h cross is taken to be 1, but they are not same dimensionally here. If they were to be same, you will be in trouble. This is a dimension of x, which is length, and figure out what should be the dimension of this quantity, and then you will figure out that k and p has a dimension which is related by h cross. So one is a momentum and one is a wave number, but we will use it interchangeably, and somebody can, a clever one will point out that dimensionally it looks wrong on the exponent, but that's correct if you don't take h cross into account. If you take into account that, that's okay. So h cross will know how small it is. Time scales, you can use seconds, but sometimes fortunately time scales will not come into picture at most of our discussions, but the atomic time scales also very small. Figure out what they are. So we will know what is the level of the length scales and time scales and mass scales that we are working on. That's something that you should realize. Then yesterday we began by saying that the interpretation of mod of psi square, as Anjali said, is probabilistic. So that necessarily means that I need to put down some statistical measures, because that is how we are going to measure. So let me just quickly write down statistical measures that we are going to use, and a very good non-mathematical and a reasonable introduction, which is not an introduction but which is just a statement of facts, is this. So what do we use in statistics? Let's use the discrete version, or I can directly use the let's say this is very simple minded, non-rigorous, and I will invite both my colleagues that if I slip in the rigor, they should point it out, saying that ultimately that is the case. But I am not going to stick to rigor, just for understanding we will say. So if rho of x is a distribution, it could be a distribution of, yesterday I said age here, it's a discrete one. So what is the age? What do we want to measure? Let us say the distribution is given, I am going to put it some curve, which is the distribution curve for variable x. It could be anything, and for us this is going to be mod of t part I have dropped. I will talk about it later. So mod of psi square, as she explained yesterday, has an interpretation. And what was the interpretation given yesterday? Let us understand that since mod of psi of x, t if you like, keep t fixed, is an amplitude, it is a complex amplitude, and I want to measure, the statement is, if I know psi of x t or psi of x 0 at t is equal to 0, I know everything about the system, provided of course I know the forces or potential acting on this. So if I know psi, if I calculate psi, it is a state function, then I must be able to compute all necessary properties whatever we measure from knowledge of this. Just as you compute all the properties if you have what we call as a phase space, which Professor Gangal will explain. That simply means that if I have in classical mechanics x of t, and I am talking about always one particle, there is not more than one particle dynamics, which goes through, and momentum. Yeah, the whole thing will go through in 3 dimensions also. It is easy to write x rather than r bar, but the discussion is general. Sometimes I do not have to write partial derivatives then, though I will write partial derivatives. So, if I have xt and pt, yes, available for all times from time t is equal to 0, the phase space trajectories, then I can compute the classical quantities. Typically, again yesterday we made a distinction that all observables, let us take 2 observables, x and p, energy E. This is what normally we talk about kinetic energy, we talk about momentum, coordinate. Total energy will be kinetic energy plus potential energy. Angular momentum, if you want to add an angular momentum later on, then there may be some more observables that we normally observe or experimentally measure. Let us take these 3 which we are familiar with. If we go from classical to quantum without any proof, we say that all these, and yesterday we explained that, will go over to corresponding operators. So, in quantum mechanics, operators, these operators, this is a function, the operators will operate on these functions, this function or any function for that matter, and we will not talk about which space and things like that. So, I need to go over from x, yesterday I said to an operator p to p operator E. If these 2 I know, I can have a prescription for converting any classical expression for a measurable quantity to energy, momentum, velocity, current if you like, whatever, a prescription. He energy, kinetic energy plus potential energy, any kinetic energy, potential energy, yes, it could be a rotational energy, angular momentum, yes. So, this will go over to some operator, and the prescription yesterday I gave, x goes to and p goes to minus I h cross d by dx. This there is no proof, we are not given any proof, say ansatz. Why it comes we will see later when the rigorous discussion which cannot be made. So, having said so much, now what do I do with these things? I am going to compute this, let us say it is that, and let us then write down some quantities that you are probably familiar with. What are the questions that you ask? First, and it's an obvious interpretation of mod of psi square that she showed in the last slide, is what is the meaning of this quantity? That is where the interpretation is, and then that will be all right. Mod of psi square.
No, dx will be outside the.
Oh, dx, yeah, of course, dx. So, dx is a small length, in 3 dimensions it will be d cube r, so it is a small volume if you like, and mod of psi square. So, this gives us the probability of finding the particle between x and x plus dx. So, that is different than this, and of course, we put a normalization condition for obvious reasons all over the space or 1 dimension should be equal to 1. So, now I ask the following question. Yes.
In place of square of mod of psi of x, if we just integrate psi of x, what will be the
Psi of x is complex. And is there any interpretation of mod of psi of x integral?
It's a state's integral. Psi of x is a state.
No, as I said,
No physical.
psi of x has no physical.
At this stage there is no physical interpretation of psi. The interpretation of psi, which took probably months or more, I do not know, is typically the Copenhagen interpretation, which says that the probability of, so mod of psi square is a real quantity, psi is an amplitude which is a state function, which is a function of x and t also. I have dropped t, we will come to t part, and this is the interpretation. Obviously, probability of finding the particle anywhere. So, mod of just psi of x has other, we will see other things, but no interpretation of mod of psi of x. Wave function has no, it has a phase, and that is another question I was, we should understand, and Professor Zog has said he will discuss the importance of phase in that question also asked why it should be complex and what is the important, it is a very important concept, phase of the wave function, and that he will also discuss, and we should understand at some stage what this stage is. So, what are the questions that we would like to ask on that? If this is a statistical quantity, then certain things we always, most probable, so if I give a distribution of age in this class, I ask a question, what is the most probable? So, that is one quantity one would like to look at, sure. Second, average, mean, and of course, average or mean, then this is what we call expectation value. This is important, that is there in the, and I like the expression for that. Average is expectation value for us. It is the expectation value which is what is measured. How to compute is our problem. All right. So, the expressions for these are exactly what you do in statistics, slight difference there. What else we do? We look at, let me write down the expressions. If there is a quantity that I want, then I standard deviation, these are standard deviation, this is what we look at. These are terms that are known to you or they are not known to you? They are known. Huh? So, we also look at, so standard deviation is known, and we will have, we will know how to compute that exactly the way you compute in statistics. No difference, except there is a minor difference. I mean, it is not minor, but there is a difference the way we will calculate it. Standard deviation, and of course, then there is sigma, sigma square, sigma. So, these all we will need when we, most important quantity that we want to do is, this is the expression that we use. So, what is that? Average or expectation, that's, but that is in statistics. In quantum mechanics it's somewhat, so operator. So, x is an operator when we go to quantum mechanics, right. The operator has to operate on the wave function. We just said for every observable, every measurement that we want to do, there is an operator in quantum mechanics. We will identify it when it comes to that. Identification, write down classical expression, convert it into operator. P and X are given, then the rest follows. We will see how to do that. Then if you want to have an expectation value or an average or what is measured for the corresponding operator O, then psi star O psi of x dx. That's the most important quantity that we want to look at always. So somebody says what is the expectation value of energy? It is this that I will compute if I know psi of x.
O corresponds to.
Yes, O corresponds to any operator that you want to measure. So let's write down a few if you like.
Quite close to the inner product, general inner product.
Well, yes, it's different than a classical one because this operates on that, and then that's an inner product between. Yeah, sure, absolutely, yes, in a proper space. So if I do this, this is operational. That's an expectation value of x. X operator and x differ only in the sense that x is a multiplication operator. It is not anything that we have to worry about. Instead of that, if I say, okay, let me complex conjugate. Complex conjugate. But it is not, look at the difference. It is not psi star, psi and x that was here. That is the difference. It is not x times psi star psi. This rho is psi star psi. This is how you would do it in probability in standard statistics. But this is how you will do it in, that's an operator. It has to come here, and that will be clear. If I put a momentum operator, momentum operator will come if I put IH cross, that's a constant. So psi star d by dx of psi, that is where it makes a difference, right?
Did you say why momentum operator became d by dx?
No, it will, no. I said take it,
Okay, yeah.
take it. Because if somewhere later part somebody will justify, he will not prove it. Actually it comes from a Poisson bracket going over to commutation bracket with IH cross, and there are two ways you can define, either x remains x or p remains p, and then you get this space and momentum space and x space representation, but we will take it, right? Would you like to make a comment on any proof on that? No. So you will take it as an ansatz. It's a ad hoc. You can take it as a postulate if you like. Right. So that will work. It satisfies certain conditions. That's the. So we will just take it. That's some. But these are the only two things that you need to take. Then if you want to write energy operator. Energy is classical. So write a classical expression for energy.
Basically, if you consider generator of translation, it comes from that.
It comes from that. Yeah, but at this stage,
Yeah, we don't
so
want
we don't want to do
So
that.
I will mention a little.
You mention that when you do classical mechanics, yes. Momentum operator can be justified or understood if you actually write down and assume that there is a plane wave solution for a particle, and then if you differentiate, you will see momentum on one side. I will show that slide, but that's kind of intuitive understanding of why it is. It's not a justification, it's a consistency check. You are not deriving from anything, you take it as it is. So take energy operator and its corresponding operator energy expression called Hamiltonian usually. It's from the name that Hamiltonian is a kinetic energy plus potential energy, and he will discuss that, and Lagrangian is the difference, but the Hamiltonian is used in quantum mechanics. Lagrangians are used at later part. So now you change this V of x is classical, so nothing happens here, it's a multiplicative normally, so local multiplicative p square, so you replace p square, so operator wise it will go to So, this will go to if you take the yesterday's prescription and substitute in P. So, it is important to retain the operator nature. So, you write P, once P, other P, d by dx, d2 by dx square, and of course, it becomes minus h cross square.
divided by
2m, that's mass, because P is 2m mass, ours P square upon 2m. So, this is h cross square upon 2m minus, do not worry its kinetic energy is minus or not, we will see what operator expression is this. You want to calculate what is measured as the kinetic energy, then we must compute, substitute O minus h cross square upon 2m d2 by dx square psi of x. First operate here, that is important. So, first operate this part, get whatever you will get another function, as operator on a function will give you a function, and then take that function and psi star and integrate. That is operationally you will calculate the kinetic energy. You want to calculate potential energy, it happens to be very simple, this is just V of x and integrate. So, it is a psi star V of x psi product integrate, psi star x product integrate, psi star angular momentum, you will write. So, we will say how do we do angular momentum? Well, angular momentum is r cross p. Now, you know r because we know x, y, z, you know p, substitute, it will become a somewhat a lengthy expression, not very difficult to compute, but then you will angular momentum is a classical quantity, write an expression which is classical and substitute these two, x for x and p for d by dx minus psi h cross. You will get corresponding quantum operator. Moment you get a corresponding quantum operator, of course, corresponding quantum operator goes here once you have that, and you can calculate most important quantity, which is an expectation value. That is our minimum that we want to do. So, that is what is measured. That means whatever you want to measure, there is an operator corresponding to that you have to figure out. That is what the whole course is about, and then you have to compute psi, which is more difficult, because figuring out operator is not that difficult, figuring out psi is, that is the wave function, is the difficult part. Moment you figure that, then most of the task is done to begin with. Is that part clear? Lot has been skipped, but operationally this is the case, right. So, let us then say, let us start saying then I had Newton's equations, I have Newton's laws, which is how the motion is dictated by Newton's law. I must have something similar here, right. Time evolution, Newton's laws are time evolution laws, right, they are time evolution. So, I must have something similar here. So, I must derive an equation. Now, I am not going to derive an equation, we are going to write the equation and justify it later on. So, first I know that I am going to write an equation for psi, and we need an equation for psi, that means I need an equation for psi and xt. Let us do that. If I need an equation for psi, so for our purpose currently you can calculate a few more quantities if you like, but let us go ahead and not get into variance and so on so forth, that we will do later on. Now, question and most important question is how to get psi. Obviously, I must have an evolution equation for, time evolution equation for, and space evolution equation for, because it has both the parameters x and t. So, just turns out that I am in the first course in quantum mechanics, which probably you will, the potentials that we are going to look at has no time dependence. Example, Classical particle placed in a harmonic oscillator. Classical particle placed in a well. That's we understand. These are model problems. Harmonic oscillator is not. It will sort of continues all the way. But barriers, wells, the well as we understand, there is a well, you get dipped into it, classically speaking. What happens if a quantum particle goes into a potential well? Just as if what we know what happens if we go into the well. Somebody has to pull us out, right? Real well, I mean. That's exactly same as what a particle means. So now I want to find out in such situations, that is how we begin, and the next part which we may not discuss is where we started with a potential which is an electron around an atom, which is a hydrogen atom to begin with, and we claim that quantum mechanics explains why an atom, the electron in an atom does not collapse. That was one of the mysteries. Bohr gave his model, but we will see quantum mechanics at the end why it happens. Fine. In general, let us generalize this. In general, if psi is xt, then mod of psi square also must depend on time. Time in general. I am not saying it will happen. There is no reason at this stage why it would not depend on time. It will turn out that it will not for a certain class of problems which we are going to study. These are, so mod of psi xt square will be time independent. We will see. That means I first have to look at a full equation for mod psi of xt, and I will write that down. What else I need to introduce before this, if there are no questions? Just sometimes in some places, not in the first course, but we will need to do that somewhere. People use in some loose way a notation which is interchanging, and finally I will state it today towards the end of the course when Professor Zog discusses, he will formalize it and go over to that notation only, not psi of x. So function of x, it is a function. I have just changed the notation of bracket, I mean just enclosed it into ket part, right. Sometimes, some other time I may use, I will say u is my state vector. There is nothing psi u, I will stick to psi most of the time, not u. If you take your linear algebra course, you will not have psi's. You will have u's, v's, anything, alphas, that depends on the abstract mathematical writer, whatever he has written. But to me, these are not interchangeable in the sense they have a specific meaning, different than what I am saying. But what I am saying is that from this to this is a notational change. From that, of course, to this is something different. But I will use this to that, so called bracket notation sometimes. Today I am going to stick to only psi of x. It is a notation change. If I can use psi of x, we understand. I can use psi of x, just a notational change, a function enclosed of this time. Then today all three are same.
Normally you don't use x with when you write a get notation.
If I try to explain why that x is dropped, that will take some time. But for us, all of them are same. Today psi of any one of this is fine. You can even use that, but because I know he is not going to use this, he is not even going to use this, but the notation remains the same, he is going to use that notation, and we will explain formally what it means. But let us get just familiar at an empirical way that there is a notational change, is more than a notational change, that will be brought in at the meaning will be brought in at a later stage. We don't need to know too much about it at this stage. So sometimes we use this is very often used. That's expectation value of x, that we also use, that notation will remain. Expectation value of p, expectation value of o. These are numbers. Are they real or complex? What do you think?
It depends on OPX. If X is complex,
Real or complex? Always, always, right? So that operator has certain specific properties. So the operators will have some mathematical property which will make sure that the expectation, yes, that's operators are Hermitian. You have done matrices. You know what a Hermitian matrix is. The same actually विसरला वाचून या रात्री आहे कुठेतरी नोट्स मध्ये आहे त्यांच्या. हा सो आहे कुठेतरी ते हा रिव्हिजनला. हा हा कारण ते घ्यावं म्हणून तो लिनियर अल्जेब्रा त्यांनी लिहिला होता ना, ते सगळं शेवटी येतं. तर दे आर इम्पॉर्टंट बिकॉज ही इज गोइंग टू टॉक अबाउट समथिंग मोर दॅन हर्मिशियन ऑपरेटर्स. ही इज गोइंग टू टॉक अबाउट युनिटरी ऑपरेटर्स. Those are the ones which are used on what you are going to learn at the end. So come up to at least Hermitian operators. You want to say something? No. So this is the notation we will all use. This for us means integral psi star x O in general, whatever may be the case, psi of x, and notation simple. Now the product notation that yes. Psi x or O psi. It's always this operates on that, and this always means it's integrated now. It's an inner product, sure. So inner product for us is an integration. It need not be integration every time. For us it's a, so we are going to use the function, so that will be an integration. In inner product space you can define inner product in various different ways. For us it's an integration, but that notation is very often used even by us because we stick to that. This is so far as the notation is concerned. I can also compute, and I want to ask a question intuitively. So these are numbers, x square expectation. So I just replace this by x square, right? Square of the operator integrated, and expectation x square, take integral and then get the number and square it. Are they going to be same?
Should be different.
in general it should be different.
Any reason? Why should it be different?
See, it's real. When you square it, it can be first complex, then you take its integral.
All right, it could be different, right? It could be same also. We will have cases where it will be same. Correct. And that is an important quantity, the difference between these two. As we go ahead, we will try to understand the physical meaning of it. The difference between the square root, you calculate that in statistics very often, probability. So that difference is important, and that is deeply related to what is going to happen in the quantum mechanics and uncertainty relation and so on and so forth. So we will come to that, and we may not come to that, but that somebody will teach that, yes. With that, let us do some simple physics. Let me write down correctly without missing any constants, the few things that you need to probably the meaning is obvious.
Probability of being capable.
Yes, and a few such other things, all right. And that is delta x. Important. The difference between square, we'll remember, give it some name, and we'll have something important. All right. Now let's go to let's write down here two operators which are very often used, which well, only one operator really, h cross upon y, yes. Somewhere here, so we won't forget. That's the one thing. P operator should be h cross upon I, h upon I. Partial, because I am taking it in 3 dimensions. That's the one thing we remember. Now exercise. X component, y component, z component, that is why partial, if P is a vector. Now exercise angular momentum operator. What is the classical expression? Classically it is right. So you have to explicitly write the product R cross P as a matrix or determinant or whatever, write R cross P and component wise separate it, classical expression, substitute, do that algebra, you will get the quantum mechanical operator for angular momentum, because angular momentum is a measurable quantity. We can find expectation values of x component, y component, z component, square of angular momentum and so on and so forth, right. That is a left as an exercise to do that. Now let us write down the now I have a question which I am not I have just question and I am going to leave it at that. Maybe not, maybe I shouldn't waste my time on those questions. If I want to represent a propagating wave, a free particle, as yesterday it was discussed that a particle with a mass m moving with a velocity v has a wavelength lambda, which we took it as the Brovie wavelength, and I want to just say it's a wave. So physically I am going to write that wave. I am going to write, of course, the real part. I mean, I write means I am just going to propagate. It's a wave with a definite momentum, so going in some direction, this direction if you like. Now this has a wavelength. I am just going to ask you the question and leave it at that. I want to ask a question, it has a very definite momentum p, where is the particle? What is the probability of finding the particle at any point? So what will you do? You will square this, and then I have just written a real part, there is an imaginary part also. I written means I cannot plot imaginary part, it is a sine plus cos. You square it and then ask this question and figure out I know exactly what is its momentum. That's why I could write it as a simple sine or cos, whatever you want to look at it. Now I square this, not just this plus, I have both imaginary part, and if you do that and find out what is the probability of finding the particle at any point x. See what is the answer that you get. Don't worry about normalization and things like that at this stage. So I am emphasizing two things, that I know the momentum of the particle exactly, and I am asking a question where the particle is. The point that was mentioned yesterday. I know the momentum of the particle exactly, and I am asking a question where the particle is. So the probability of finding the particle anywhere in, well, just find out at some point and see what you get as an answer, okay? And then we will discuss that, or somebody will discuss that, why it happens. Yesterday also I gave contrasting example. That is a packet, sometimes visually it is shown with that. That is where my particle is. That is how we started saying that normally we would like to represent a wave function as a wave packet. I will leave it at that. I contrast that with what I wrote. Now let us write down the equation. Write down the equation. I am not saying derive this equation. There is some justification. If time permits, we will do that. As I said, in 90 minutes, this is not the case. So we will begin by writing equation which is famous, Schrodinger's equation, time dependent, because I need to find out the time evolution and space evolution or changes of both psi of x at t. The equation is the following. I will just describe the characteristics. That is the left hand side, and I will make the comments later on. I will leave if it is x. Have I derived it? No. I'll show some slides for some justification. Let us look at the characteristics and we will discuss when time permits later on, when time. Oh, very important. Yes. If I miss an I, you are going to die. Then I will get a solution. It is obvious. If you look at the differential equation, I will get a solution which is not oscillatory in energy and it is decaying. We do not want decaying solutions. So yes, that is a very important. This is linear in t, left hand side is the first derivative, and that one simple reason is just as x and p in classical mechanics determines there are two conditions that are required. At time t is equal to 0, I must know x, I must know p, then I have an entire evolution. I do not need anything else, Newton's law. Here I have a state function which is one just state function at time t is equal to 0 and of course x at other values. That determines everything. That means it will evolve. I can take a linear combinations and what not, but if it evolves, then it should evolve linearly with a linear operator d by dt, just one side, that is all. This if you look at carefully, that is classical to quantum kinetic energy. If you look at that, that is V is a potential energy. So the operator wise it is p square upon 2m V, which is so that is an Hamiltonian. So this of course, so on this side I have, on this side I have H It's an Hamiltonian operator. It's time dependent. So I must write T explicitly. A deeper justification for this was obviously not arrived at a simple 1 hour class. People must have debated, discussed mathematical conditions, then arrived at this. After Schrodinger didn't just do it in this way, but we will skip that part. Otherwise, we will spend more time, less operational time. That's time dependent Schrodinger's equation. In principle, this is all what you need to solve. Given potential V, which is not time dependent. Of course, in principle, even this, of course, I must write, yeah, that is time dependent. It can be. Where it can be time dependent comes if I apply to a system, which we will do very often, a time varying electric field. That is one standard case. If I apply time varying somebody talked about NMR and so on and so forth. If I apply time varying electric field, then the potential is time dependent. The life is more complicated. We are not going to make that complication. We are going to say that we will deal with potentials in the first course, where V, the potential is time independent, right. So, under the condition that what happens, that is a time dependent wave function, and I want to, that in general is of course this, and this has, if I have this as a general solution, but if I take V of x t, time dependence is gone. The ones which I stated, a harmonic oscillator, static potentials, potentials that we experience when you walk here, there is a barrier, that is a potential, that is a repulsive potential, and so on and so forth. Hydrogen atom, that I started, a proton minus Z by R is the potential that a proton gives, Z being 1. It is an attractive potential, 1 by R, R is the distance, that is a static potential, it does not have a time dependence, an electron moves around that. The characteristic is, although Earth moves around Sun, its orbit is not stationary. Here we claimed we know that since we exist, all of us, the electron in any atom does not go and collapse on the nucleus. So, it is stable, we will see why. So, under the condition that that is the case, this equation has the solution. Not going to derive that either. It happens that I can write this is not necessarily, this you can check whatever the SPI splits. So, standard mathematics, then I will get an equation and a solution of this kind. phi which is dependent on x, psi is dependent on x, phi which is dependent on t. So, you get two differential equations, one for x, one for t, one for psi and one for phi. Phi part you can solve analytically, minus I E t upon h cross, where E so far is a constant, it is energy unknown, and minus h cross square upon 2m, that is, so this part is h and that is energy, same energy appearing here. The process is, this has no time dependence, this is a full, so I will write the 3-dimensional part corresponding to that. That is similar, minus h cross square upon 2m if the potential is 3-dimensional, d2 will go over to del square plus no time dependence. 2 dimension, 2 dimension, 3 dimension, 3 dimension, I still have the del square operator there. That is still partial there, because potential is not, potential in general is dependent on a vector r, which is normally the case. Characteristics, linear of course, that is kinetic energy term, but look at the way this function has, this equation is different than standard differential equations. If I write it in the form which is h, which is this and this term on psi, that is what Professor Kshirsagar was saying. This is very different than a standard second order differential equation. It is a differential equation which must be solved, but it must be solved with something different. An operator h operating on this function psi gives me the same function psi with a constant e. That is different than saying that I have second order differential, standard second order differential equations, not partial. How many solutions it has? The question is tricky. So, how many solutions it has? How many? That is where the physics comes. What is the boundary condition? We will just in a moment see what happens.
So his solution has this form.
Paune 11.
So the solution has this form at psi equal to E psi.
This is not the solution, this is the equation. I have just written in a compact fashion. This means this h cross square upon 2m.
This is equivalent to solving this.
This and these are same.
Yeah.
I just wrote in a compact form to make sure this size here, size here, size here, E is a constant, Vx is known, psi is unknown. The only quantity unknown is a pair. So, we are talking about a pair psi x paired with E. I might write E here if you like. So, they always go in pair. That is an eigenvalue and this is an eigenfunction if it is a solution of that equation. So, if I solve this equation, I get a state function which is an eigenfunction and then I get an eigenvalue which is of course the allowed one of the energy levels or energy. It is not one, we will see it is not just one. Any set psi E, I could have E1, E1, E2, E2, E3, E3, E4, E4 as we will see what happens. You know matrices, an n by n properly formed matrix has n eigenvalues. Every matrix does not have, but so it can have n solutions. So, finite dimensional n by n matrix can have n eigenvalues and n eigenvectors. This is that eigenvector, eigenfunction, you can name it in any way fashion. I have not written it in a matrix form, it is a differential equation form. It can equally be written in a matrix form of course, but this is in a differential. So, I need to solve a differential equation. A differential equation with the eigenvalue problem of this kind is solved with a boundary condition which comes from physics, and I will tell you how that can be realized. But an interesting thing is psi you understand this? If I find an eigenvalue E, then my full wave function which is x part and time part is the product. The second part which I wrote here phi, that phi is known. Do you understand that? Everyone understands that, because this is crucial now. I have solved the time part. If I know E, I know exactly how the wave function evolves in time. So, I do not ever solve time evolution, it is analytically known. I need to solve eigenvalue. If I know E, I have solved that. Mod of this square,
This part will go away.
correct. So, mod of this square is time independent. So, such states for which mod of x t square is time independent, note they are called stationary states. They do not, the probability, they do not change. Wave function changes in time. Wave function is not time dependent, independent. Wave function does have a time dependence always. It is complex. Even if psi x is real, I could have places where this psi x is real. In fact, that is what we will see. But psi x t, the total wave function is complex, but mod of psi square this is time independent. So, the probability density or probability of finding the particle is constant in time. It does not change.
Physical meaning क्या हुआ? What will be the physical meaning of this?
Well, instead of me giving an answer, I am going to press you to give an answer. So, my electron revolves around, okay, let me complete the next part and we will come to this. So, that means whatever may that
Why electron does not collide? Yes.
will come, yes, I mean sure, one by one coming to that, but rho of x is the, if it is an electron, it's the probability density. If I multiply it by charge, it will become charge densities. We will call it charge density, but we will say probability density. So, probability of finding the particle at between x and x plus dx for any time ever is the same. We are not yet there, we will see where it is. It is a stationary state. That is why it is a stationary, the state is stationary. That does not mean that psi is time independent, time has a time dependence. Okay. That is first. Now, our task, I will come to this, we will see that d rho by dt can be shown to be 0. You can analytically show that d rho by dt is 0, that is it's a constant in time, and the other properties. But the task now that we want to do is this, how to solve that. So, let us discuss physics of that. For a simple case, anyone wants to make anything I have missed here? You can make some, I mean, unless it is a very subtle point. We do not want to discuss subtle points. Yes, it is okay. Any questions? So,
equation can be obtained by time translation signal. E raised to I h t.
A generator, yeah, it's best to avoid.
yeah, sure, no. Sure. I mean that probably towards the end sometimes, yeah, sure. Right now let us take the equation as it is, and sure. So, operationally what is quantum mechanics for us in the first course? Most of us will take V of x to be independent of time. Okay. So, we deal with this, and it is always written h psi is equal to E psi, or that. Further, for simplification, not really simplification, most of us, though I should not use it in first course, will use h cross square as 1 and mass as 1. Mass of, if it is a mass of electron, but if you want I will retain it, it is easy for me to sort of. So, that becomes half of, that is the unit I am using if you are dealing with electron. If you are not dealing with electron, you will not use. Those are formal correct units, it is not arbitrarily taken to be 1. You can't take everything to be 1. Normally we will take velocity of a light c to be 1, we will take h cross to be 1, we can take mass of electron to be 1, means your mass is measured in terms of your correct electron mass. So, these three at this stage is fine. Bohr radius is taken to be 1.
If you are taking atomic units, then C will not be 1.
Then C will not be 1. Velocity of C, yes, sure. Atomic unit C will not be. Time also has some funny units. It is an atomic unit of time, but normally here will not come across unless I start talking about Bohr cyclotron frequencies and things. So, this is where the crux is. I want to solve this, and I add, you can't plus a boundary condition. That is very important in physics. Now, we will see what boundary conditions. Boundary conditions on what? Boundary conditions on wave functions. So, we are going to deal with the problems where E is a constant. It is a real constant. This is real. Some funny examples we make sometimes for students. What happens if V becomes complex? Just think about it. What will happen? Later stage. I want to solve this differential equation. and we are going to take the case which are called bound state problems. So there are two kinds of problems that we come across. One is normal scatter. Yes. Oh yeah, of course. So bound state problems. So I have two kinds of things we encounter. Scattering, which we know, we are not going to deal with that. So an electron comes, gets scattered from a nucleus. Those will be dealt with separately. Another kind of problem is equivalent to Earth going around a. So it's a bound state problem. So what is the characteristic of bound state problem? Very simple, is that the probability of finding that particle outside a certain region is 0. It's bound to certain, I am giving a physical, it's bound to a region. How small, how large a region, we are not talking about. Okay. We are just saying, and mathematically of course it can be made more precise, and that I am not going to make it now. It has to be made more precise, but that we will do later. Okay. So, wave function must go to 0 as plus at x as boundaries, whatever, in general the boundaries as x goes to infinity, right. Wave functions also has certain characteristics that she mentioned. It should be continuous, differentiable, no spikes, no discontinuities, will not go to infinity, smooth,
Single value.
single valued, yes, that is very important, single valued.
Should be a nice looking function.
Well, I would be happy to make as nice looking, but then the mathematicians will not state the conditions, right. So, is this an acceptable wave function? So, discontinuity and so on and so forth. So, you can draw and find out that going all the way, no, not square integrable as they would say. So, since the bound state, we put the boundary condition that this is, that is my boundary condition. So, I want to solve the differential equation with this boundary condition or a suitable boundary condition, which is of course similar to this. It does not violate this at least. Let us take one example. And let us first discuss it intuitively, then we will solve the differential equation. That is a potential well where the walls are going all the way up to infinity. Yeah, 11:30. Yes, yes. So I will just discuss next half an hour and then give it to him. T.
आणि आता आज तुम्हाला थांबावं लागेल.
आज थांबायचं हे दोघं जण आहेत. Yes, yeah, sure, sure, sure. So this will discuss, I mean they will discuss after me, someone. My lecture. Yesterday मला अर्धाच तास मिळाला. काल मी अर्धाच तास, म्हणजे दीड तासाचे 2 होते. Okay, T. उद्या माहीत नाही वेळ मिळेल का नाही. त्या गांगालांचं पण असेल, त्याचं आहे, तुझं पण आहे ना उद्या.
नाही तेच मला आता मी उलटं बघत होते.
हे घेतलं आता संपलं की माझं, आता तुला उरलेलं घ्यावं लागेल. तू इथनं कंटिन्यू कर ना, कारण संपलं ना, संपलं. हेच ते पुस्तक जे मी वापरतो.
आता तुमचं झालंय का? यू स्टिल हॅव अनदर हाफ एन आवर?
नाही, आता ह्यांना काहीतरी मिळणार नाही मग.
ओके. So then you'll pause out here.
I'll pause out and she will continue when she takes tomorrow
You'll okay.
from this place.
चालेल. आणि मग तुम्ही टी ब्रेक
आता हे टी ब्रेकच्या नंतर
तर तुम्ही घ्या. So आता किती
11:30 झाले असतील ना?
सव्वा अकरा.
पावणे बारा 11 येते.
पण नाही 11:30ला सुरू करू
11:30.
11:30 सुरू
आणि मग 1 पर्यंत तुम्हाला 1.5 तास होईल.
मग जेवण आहे
तुमचं दुपारी
हे बंद करायचं
रनिंग 1
पुस्तक आणलंस
1.5 तास
मी अरे ग्रिफिथच आहे हा
बस काही झालं.
बाकी काही उगाच त्यांना हे नाही करायचं
पण कमी घेतलंय पण काल कंटिन्यू करता आलं नसतं असं मला वाटतं.
3:30 वाजले असं सगळ्यांनी असं हात वर केले हे याला माझं नेहमीची फुली असते ती कुठे गेली
गुरुवार शुक्रवार there's one person who is going to present next week. He is unable to come next week, so then
हाँ.
we'll shift Umakant.
आपण
Yeah. So he's not here next week. He's coming. I think Tuesday, Wednesday, Thursday. RP Singh. पुढच्या आठवड्यात. Yeah.
गुरुवारी
हे याच्यात
माझं एक होतं
Yeah. So we,
हाँ.
so we can postpone to next week.
फ्रायडे
नाही, next week. चालेल.
नेक्स्ट काय म्हणजे मला फक्त वेळ सांगावी लागेल कारण
Okay.
I'm busy on Monday and Wednesday.
I'll come and
ते काय
take the data.
इंडिपेंडेंट टॉपिक आहे स्टॅटिस्टिकल मेकॅनिक्स आहेत ते दोन
Right.
कॅन
We
बी
can adjust.
पोस्टपोन
Then there are other lectures we can shuffle around. So that's okay.
सर
नाही मला पुढच्या आठवड्यात चालेल फक्त मंगळवारी वगैरे चालेल मला.
Solid. Okay, please.
सर लेट अस नो
Right.
which day
चला
मी पण नाही सांगितलं डायरेक्टरचा कॉल डायरेक्टर म्हणाले मीटिंग जॉईन करा मी
Meeting.
हो ते इंजिनियर फॅकल्टी इंटरव्ह्यू चालू
Okay.
सोसायटी
नाही मागचं पण आम्ही जे QT05 चा एक FTP घेतला होता त्याच्यामध्ये तेच होतं की FTP चालू आहेत आणि इकडनं फोन येतात की अरे तुमचं जॉईन करा हे करा ते करा. Yeah. क्या
येस विल गो त्या लोकांना कम्युनिकेट करावं लागेल का काय करायचं ते कोण देत आहे तुला किती बाया घेतो जरा माणसं. तुला वाटलं ते किती आपल्याला
ट्रिपल आय टी एक प्लस पॉईंट आहे ट्रिपल आय टी वर्सेस मध्ये इथे गोष्ट आहे
गेट पण जाईल. पण ते लागते काहीच नाही तिथलं वाटते काही अडचण नाही.
तर नाही तर मग करू शकते
तिथे
ते
म्हणजे
म्हणजे
बेटर काही मिळाली याची तर काही शक्यता नाही.
कारण आपल्या इथे एकच दिवस मला नाही लागत आहे म्हणजे पण मला ह्या वेळेस नाही मिळालं शिरोली लागणार ना मला घ्यायचं तर मी पण घेणार अजून मुद्दा बोलतो तुम्ही आम्हाला काय रिपोर्ट पाठवून द्यायचं आहे ऑनलाईन ते मला अपलोड करायचं आहे पण आता कसं आपल्या सगळ्यांची साईन झालेलं
ऍक्च्युली सरच घेणार आहे ते. मला ते वर्षात याचा पिक्चर सुटला ना माझा या वेळेला तर देशपांडेला म्हटलं अरे काढा तिला माझ्या देशातून काय होणार नरडीला बसून ठेवले तिला सोमेराच्या तिला काढलं यावेळेस काढलं का ते घेतो ना
काल तेव्हा नाही का पोराला एवढी बडबड करत होती मी तर फोनच कट करून
त्याची मॅड
झाली पागल
खरंच पागल झाली.
सगळी बाजूने आपण गेले कोणच नाही
काय म्हणतो
बघतेच तुझ्या तू कसं काय कॉन्टॅक्ट टाकला मी बघतेच मध्ये टाकला काही जनरेटिव्ह वेगळं ठेवलं होतं म्हटलं कॉन्टॅक्ट गिरीश सर हॅलो सर तेवढ्या त्या साईन कर ना मला पुढं पाडव एखादी तुझी साईन एक कर कॉपी कर आणि फक्त टेस्ट कर ना बाकी काही नाही हां का सगळं झाल्यानंतर कर ना काही प्रॉब्लेम एक काय कर साईन नाही काय कर तू इन्सर्ट कर फक्त एक कॉपी कर म्हणजे आपली साईन केली ना त्यात फोटो काढ छोटा पेनचा तेवढी साईज हा तेवढं तेवढं डायरेक्ट पेस्ट होतो मेल पाठवला नाही तुला ऑलरेडी मेल व्हॉट्सअपमध्ये ना ओपन कर फक्त तिथं पेस्ट कर कारण आम्हाला ते पुढं अप्रुव्हल न पाठल्याशिवाय आम्हाला अपलोड नाही करता बस
अरे तुझी सीट वरून देऊन टाकली आहे का? एक पोरगी आली तुला सही
मी
त्याच्यावर मी
म्हटलं
टाकलं.
कर हा
सही करायला मग मी त्याला पुढे सजेशन दाखवले मी म्हटलं हे अरे काहीतरी सजेशन दाखवलं करेक्ट
इंटर्नशिपला आली असेल ना
करेक्ट
गेंजी
करायला पाहिजे अरे करेक्ट करायला ओके सर सब्जेक्ट पण सही दिली तिला
नाही दिली तिला वाटलं कर नाही मी पुण्याला
ती गेली ती 5 मिनिटांमध्ये काढून घेऊ मी म्हटलं सही कुठे याची सही कशी मिळाली ते उसने भेटते काय ग्रेट आहे तो ओळखी म्हणजे काय बायको त्याला काय आहे का? पण तरी काय ऑनलाईन डेटा एवढं सह्या एवढं देऊन
नाही
टाकायचं.
ते हे दिली तिला याची
आज शाम के लिए ढूंढना पड़ेगा
फोन कर रहा हूँ
अच्छा उधर जाएंगे क्या
नहीं जाएंगे नहीं वो तो चली गई है काम
अच्छा
नहीं उसकी बेटी नागपुर में रहती है उसको फोन कर यंग है तो आसपास का पता होगा इसको तो पता नहीं होगा
गैस पानी बहुत कम है कल अच्छा था वो मिशन वाला मतलब अच्छा लगे सब लोग बैठे थे चतुसंगी अब यहाँ का सर अलग डिश अलग खाने का क्या है जो नागपुर का नहीं है या टेस्ट अलग हो नहीं या फिर टेस्ट अलग हो या फिर कुछ अलग जैसे आपने वो मोदक बोला है वो दिमाग में है मेरे
यहीं पे एक आइसक्रीम भी है बहुत अच्छा है
अलग है
यहाँ का फेमस लेकिन अभी बारिश इतनी है तो आइसक्रीम थोड़ा
थोड़ा अवॉइड करना है वो भज्जी बोला कब लोगों ने भज्जी खिलाया था
हाँ
हम लोग
आज
तो
टाइम
मुझे लगता है अभी 2-4 साल और लगेंगे मुझे अभी याद आने लगती है चीज़ें
हाँ।
भूलने में
Yes.
दिल्ली का है मेरे को क्योंकि ये डिफरेंशियल इक्वेशन से वी गो ऑलवेज गो टू दिस ये पढ़ाया था
हाँ नमस्कार सुनील भट बोलतोय VLI कडून.
एक
हो, भेटलो होतो.
दिल्ली में सर थे
आज रवींद्राशी बोलणं झालं
जब ये पढ़ा
हा भेटलो होतो येस
वो सब पढ़ाया है डिफरेंशियल इक्वेशन से कैसे कन्वर्ट करते हैं
तुम्ही तुमचा जरा सायन्स एज्युकेशन मध्ये इंटरेस्ट माझा पण आहे
इलेक्ट्रॉनिक
तर आपण भेटू शकतो लंचमध्ये वगैरे.
हां.
हो.
कोडिंग
नाही नाही, आमचं अरेंजमेंट आम्ही त्या इकडे केली आहे, सदानंद बाबा मालके गेस्ट हाऊस महाराष्ट्र सरकार. ते एक महाराष्ट्र कॅटरिंग अँड हॉटेल मॅनेजमेंट इन्स्टिट्यूट अशी घेतली आहे. हां JW मॅरियटच्या हां आहे, म्हणजे असं काही प्रॉब्लेम नाही आहे. 4:30च्या आसपास संपतं. हां 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 येस येस. हो चालेल. नाही आहे, आम्ही 17पर्यंत पोहोच आहे. हां सॅटर्डेला नाही. पण म्हणजे वन टाईम आय कॅन ऑलवेज गो बॅक बाय ऑटो, असं काही इश्यू नाही. हां 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 बरोबर. हो येस दॅट इज गुड. कारण म्हणजे दोन गोष्टी आहे. एक तर मी स्वतः 5 वर्ष राजीव गांधी सायन्स अँड टेक्नॉलॉजी कमिशन जे आहे, काकोडकर साहेबांचे अध्यक्ष, त्याचा मी मेंबर होतो 5 वर्ष. हां आणि दुसरं म्हणजे मी विज्ञान भारतीसाठी पण काम करतो. तर त्याच्यामध्ये आमचा हाच इंटरेस्ट आहे की प्रमोशन ऑफ सायन्स टू मासेस. हां बरं बरं ओके. हां हां ओके ओके ठीक आहे. मी सांगतो तुम्हाला काय, माझा काय मुलगा इथे राहतो पुण्यात. एकदा त्याच्याकडे जायचं आहे. पण लेट मी चेक आउट कसं काय होईल. आणि मग डेफिनेटली विल हॅव सम टाईम टू लिव्ह. हां हो सुनील भट. हां हां येस येस. हां हो येस. हां आता मध्ये लेक्चर ब्रेक. हो येस.
त्याच्या सूर्य कॉलेज से भी हुआ क्या बात?
हाँ सूर्या बोले से बात कर सकते
बाजू में है, जब हम चले जाएंगे ऑटो से.
हाँ
हाँ. हाँ, GP चलो.
लेक्चर होगा ना
ये हम लोग को थोड़ा करना पड़ेगा. मैंने उनको भी बोला कि बेसिकली एक सीक्वेंशियल इसमें लॉजिकल सीक्वेंस में जो नोट्स हम लोग कभी हम लोग राइटिंग डाउन विल नॉट है. हाँ
नहीं
LMS के लिए भी उनको चाहिए नहीं.
LMS में ये सब नहीं.
हाँ नहीं डालते.
LMS is very like simple.
हाँ
Chandra, but we will verify because we also do.
सर उगले सरांनी तुम्हाला डिपार्टमेंटला इन्व्हाइट केलं आहे.
अरे वा. याचं तर आहे हो ते.
तुम्हाला मी एखादं म्हणजे
नाही, इथून 4:30 वाजता आपण सुटलो की आपण जाऊ शकतो.
हो हो
तसं करूया.
हो हो.
कारण मलाही सरांशी भेटून बहुत दिवस झाले.
प्रमोद जी, वो एक QT
पांडे सर आमचे एक मित्र होते खास.
प्रिंट आउट चार्ट
जैसे मैथ्स के सारे फॉर्मूलाज के लिए
हाँ
वो अपने print
राहिले नाही विचार.
आपको मेल पर किया है ना?
मेल पर किया है, but
ठीक है,
when
उसमें
we switch off,
पहिल्यांदा त्यांनी मेसेज केले तेव्हा आता आम्हाला हेच वाटलं की तेच गेले की काय.
तो फी
डिवाइस
हा कारण त्यांची तब्येत पुष्कळ बरी नाही.
क्योंकि मैंने दो सर से बोला है
त्यांच्या मिसेसची बहीण पण गेली नाही.
बैक टू बैक लेना ऐसे
ते नागपूरला होतं, आम्ही गेलो होतो त्यांच्याकडे. Also pass
आप
गेले.
10 ले आओ एटलीस्ट जिसको चाहिए होगा
हे तर बिचारे म्हणजे काय म्हणतात सज्जन पुरुष साधू पुरुषच होते, कोणाला काही दुखवायचं नाही काही नाही. ते नाही म्हणणं यांना शक्यच नाही राहायचं असा प्रॉब्लेम. म्हणजे त्यांच्या मुलगा जेव्हा मला असं वाटतं फुल मॅच्युअर झालं रिमेंबर तेव्हा फोन आला की असं असं आहे ते त्यांना जायचं होतं तर तेव्हा कसं सांगू ही इमर्जन्सी आहे याला की तुम्हाला आता सोडूनच जायचं आहे जा आणि आठवड्याभरानं या म्हणजे तुम्ही विचारा सर काय असे राहणार सर सरांना घाबरायचे तर मी नाही घाबरायचो. मी त्यांच्या अंडर नव्हतं पण मी ते माझ्या RPC म्हणजे रिसर्च कमिटीमध्ये आणि आय यूज टू डिस्कस विथ एव्हर लॉ. त्यांच्याशी माझं एकदम चांगलं होतं. म्हणजे आम्ही त्यांना सांगितलं काही प्रॉब्लेम काय म्हणतात लॅब असतात ना म्हणून त्यांना जरा लोड होतं की आता लॅब आहे हे काही नाही हे फर्स्ट प्रायोरिटी आहे. म्हणजे विचारायचे इतके हे होते म्हणजे सज्जन नको इतका सज्जन माणूस होता. तुमचं काय ना
मी नागपूरचे.
अच्छा तुम्ही तुमचं कुठून झालं
मी सर बी रामदेव नागपूरमध्येच केलं पांडवपूरला.
अच्छा
आणि नंतर CA घेतली आणि PhD IT कॉमर्स.
अच्छा कोणाच्या
सुभाष चौधरी.
बुराण
दोघांनी
ते आहे मॅडम पण आहे ना हां बी हां काहीतरी बी किंवा
त्या बैरज सरांसोबत.
अच्छा टेस्टिंग झालं तर मला मोठं झालं अर्ज केला होता माहिती आहे ओके क्लासिकल मेकॅनिक्स
तुमच्याकडे ते प्रमोशन आहे
जर्मन्स वगैरे
हो हो.
राहणं कुठे आहे म्हणा
गाव माझं सामाजिक कामात
काकडे सांगायची काही नंतर ते काकडे तो माझा क्लासमेट बरोबर त्यांची इच्छा होती काही
हो हे चालूच आहे.
चालूच आहे का काय मी ते दाखवत जाणार आहे.
हो, हे पण
मग
आहे.
एक्सप्लेनेशन बोर्डावर देणार
या
नाहीतर
So,
ते 1.5 तासात संपणं अवघड आहे.
हो
त्यातली एक PDF फाईल आहे तेवढी.
या
किती दूर आहे
बाउंड्री कंडिशन्स
हां
हे किंगस्टन
हां
हॅमिल्टोनियन डायनामिक्स
Correct.
ओके
ती PDF
PDFच हवं
हां.
आहे ओके आणि हे फुल स्क्रीन करू
हां चालेल ते आता इथे लोकांना कसं दिसतं मला माहिती
या
नाही.
विल सी
आणि
ओ
मग
दिस इज
कसं झालंय?
रोटेटेड ओके सो लेट मी नॉट ओ
उलटं झालं.
ओके 1 सेक सो हे
परत आणून ठेवलं आठवड्याला एक दिन जायचं.
सो हाऊ इज इट ओके वी नीड टू टर्न ऑन
पहिले सुरुवातीपासून
हां एक मिनिट
आणि शेवट काय येतो तो हे बघू.
सिंगल पेज फुल स्क्रीन मला दिसत नाही आहे
नाही दिसत आहे.
एक मिनिट
तू वरती ढकलत राहील.
या ओ या स्लाइड शो ओके गुड ओके सो या दिस इज हाऊ इट विल लुक
हां पण ते तिथे कसं दिसतंय माहिती
ते
आहे?
ते करूयात I'll turn that on.
It's an eigen value. If it's an eigen state, you will always get it.
मग एक्सप्लेनेशन बोर्डावर
पण मग ते स्विच करावं लागेल म्हणजे आधी
मी
तुम्ही
Again and again करून नाही येणार.
मी असं एवढ्या
सो
दोन बाजूला दिली.
दोन बाजूला विल यू बी कम्फर्टेबल विथ दॅट
काय
मी टॅबलेट कनेक्ट केलं तर त्याच्यावरती लिहून
पण असं नाही बोर्डावरती
आय
लिहिलं
थिंक ते सेटअप करत
कसं झाली
Interpretation, expectation
कागदावर लिहिण्यासारखंच आहे.
हजार
नाही तर झालं.
त्यांनी measure केलं.
but if it's the first time it becomes a little bit okay here we go
दिसतंय का नाही वरती वरती पहा सुरुवातीला सुरुवात आणि शेवट